Imagine you're piloting a drone
Right.
and it's navigating through a collapsed building.
Yeah, incredibly high stakes.
Exactly. And its spatial sensors are flawless. The AI model running it is state of the art. But then suddenly, the entire system just goes completely dark. It crashes.
And most people would immediately assume the software failed, right?
Right. But it wasn't a software glitch. It crashes because a microscopic cluster of misaligned adders in the silicon actually warped the physical wiring. It spiked the temperature and literally melted a data pathway.
Which is a catastrophic hardware failure at the most basic physical level.
Yeah, and it takes the whole drone down. Okay, let's unpack this because today our mission for this deep dive is to explore a massive stack of architectural blueprints and research papers. They're all detailing something called the precision node.
Right, the precision node.
Yeah, and it's basically the highly anticipated blueprint for next generation cyber-physical systems, or CPS. And we're going to see how the era of relying on just one single magical breakthrough, whether that's in software or hardware, is completely dead.
It's totally dead. If you look at the source data across all of these papers, you see the fundamental mistake engineers have been making. They're trying to optimize things in isolation.
Like treating the hardware and software as totally separate worlds.
Exactly. You can't just slap a brilliant, mathematically flawless software algorithm onto physically fragile hardware. It just doesn't work. And conversely, if you design this impenetrable self-healing hardware layout, but then you force it to run incredibly bloated, inefficient code,
the system still fails.
the battery drains, it overheats, it fails. To build a true next-generation CPS, the optimization has to ascend the entire stack all at once, from the physical wiring up through the cryptographic security, all the way to the algorithmic compute.
Which brings us to the ground floor of this precision node blueprint. Layer 1, the physical interconnects.
Right, the actual roads the data travels on.
Yeah. And the bottleneck here is just pure physical geometry. The sources focus really heavily on the shift to 3D ICs. Because traditionally, we lay out silicon dies flat right next to each other on this massive, sprawling motherboard.
Like a huge flat city.
Exactly. But with 3D ICs, you stack them vertically. You connect these layers using these microscopic vertical tunnels drilled straight down through the silicon. They're called through silicon vias, or TSVs.
The geometric advantage of doing this is just staggering. I mean, when you stack chips vertically, you're literally altering the fundamental physics of how data travels.
Because it doesn't have to go as far.
Right. In a traditional 2D layout, signals might have to travel all the way across the board. But in a 3D IC, the average wire length becomes proportional to the square root of the layer count.
Wow. So you drastically shorten the physical distance.
You do. And that gives you massively higher bandwidth, a really sharp drop in power dissipation. And it enables what we call true heterogeneous integration.
Meaning you can mix and match different types of tech in one stack.
Exactly. You could have a layer of high-performance logic processing, bond it directly on top of a high-bandwidth memory tier, and then put, analog sensors right on top of that.
But, and here's the huge catch, the manufacturing reality of this is absolutely brutal. Drilling these tiny TSVs through solid silicon is, it's highly susceptible to failure.
Oh yeah, it's a nightmare.
You've got via etching, you have to fill those holes with conductive copper, you're thinning the wafer down, and then thermal bonding. At any point, things just go wrong.
And there are so many types of defects.
Yeah. You get open defects where the copper filling leaves voids or microcracks. You get short defects where electricity leaks straight out into the substrate, or the thermal bonding pressure is just slightly off, causing severe geometric misalignment between the layers.
And you have to remember, a single post-bond TSV failure can render an entire multi-die stack completely useless.
It's like an elevator shaft in a skyscraper, right? If the shaft is fatally misaligned on the 13th floor, the transport for the entire building is just ruined.
That is a great analogy. And you end up with a multi-million-dollar wafer that immediately becomes a paperweight. But what's fascinating here is how we used to think about these defects.
What do you mean?
Well, historically, engineers treated these defects like lightning strikes. They assumed they were just uniformly random across the chip, just bad luck. But the latest empirical data proves that defects are actually heavily clustered.
Right, because of the physical manufacturing stresses. I mean, a variation in bonding pressure doesn't just mess up one via, it crushes that whole microscopic neighborhood.
Exactly. And the research introduces a specific metric for this called the clustering coefficient, denoted as alpha.
Okay, so what does alpha actually tell us?
The higher the alpha, the more densely packed the failures are. Basically, the probability of a via failing is inversely proportional to its physical distance from the center of a cluster.
Ah, so if you have a void in one TSV, the physical stress that caused it probably fractured the 3 or 4 vias right next to it, too.
Right. So if that's the reality, how do you bypass a clustered physical cluster bomb of damage?
Well, the old method was just adding redundant PSVs, right, like spare lanes on a highway. And they'd use multiplexers to switch the data traffic over to the spare lane if the main one failed.
Yeah, that was the standard fix.
Yeah.
But if you're using traditional routing architectures like a simple chain or a one-hop cellular model, they get completely trapped by these clustered defects.
Because the spare lane is in the same neighborhood that just got wiped out.
Exactly. If the entire neighborhood of wires is crushed, having one spare right next door does you absolutely no good.
Which brings us to the blueprints for the precision node and how they introduce LCTRA cellular TSVs, because LCTRA just totally abandons that simple shifting idea.
Right, it brings in advanced graph theory to solve a purely physical routing problem. It relies heavily on Menger's theorem and this concept of vertex disjoint paths.
Okay, we need to break the mechanics of that down for the listener, because, vertex disjoint paths sounds incredibly abstract when we're talking about actual copper wires.
Fair enough. So Menger's theorem essentially states that the minimum number of nodes you have to remove to completely sever a connection between 2 points, that's exactly equal to the maximum number of mutually independent paths between them.
Okay.
So a vertex disjoint path is a route between point A and point B that shares absolutely 0 intermediate nodes with any other route.
Got it. So by designing the TSV grid to support multiple vertex disjoint paths, the system basically guarantees that even if a massive defect cluster takes out a huge chunk of the grid, it cannot sever every available detour.
Exactly. It mathematically ensures a path survives.
It's like a city grid where a massive sinkhole takes out 3 major intersections at once. You don't just shift into the lane next to the sinkhole. The GPS calculates a vertex disjoint path, routing you like 4 blocks around the perimeter, ensuring you never even touch that compromised neighborhood.
That's exactly it. And the hardware execution of this is fascinating. LCTRA uses a specialized switch-based matrix.
How does that work in practice?
The multiplexers are designed to default to their current node for transmission. They actively evaluate the network, and they only pull signals from adjacent nodes if that specific adjacent node lies on an established replacing path for a faulty via.
So it bypasses the distant, fault-free vias entirely.
Right, meaning it doesn't add any unnecessary base delay to the healthy parts of the chip.
Okay, but surely routing around a sinkhole isn't free, right? Detours have to add signal degradation.
Oh, they definitely do.
Yeah, the sources say if you force a signal to take a 400 micrometer reroute around a cluster, you're adding about 200 picoseconds of wire delay. And the multiplexers themselves add latency too. A 14-to-1 multiplexer adds roughly 340 picoseconds of gate delay.
And in a processor trying to execute billions of operations a second, those picoseconds compound into a massive performance bottleneck.
Right, so how do they fix the delay problem?
That signal degradation is exactly why the LCTRA system pairs with something called adaptive fault tolerance, or AFTS.
Okay.
AFTS doesn't just blindly connect the first available spare path it finds. It uses a mathematical optimization model called integer linear programming, or ILP.
ILP, right.
ILP evaluates the specific, non-uniform layout of all the functioning and spare vias on the fly. It sets up an objective function to minimize the global multiplexer delay across the entire chip.
So it looks at the whole board.
Right, constrained by the available healthy nodes, and it computes the absolute mathematically optimal repair structure.
And the performance metrics for this are just a total game changer. The blueprints show a built-in self-test architecture, a BIST, that lets the chip autonomously detect these clusters, run the ILP optimization, and literally record the repair signatures into fuse registers.
Which is incredible for manufacturing.
Yeah, it cuts test time by 17.5%. And for high bandwidth memory stacks, which are notoriously sensitive to these cluster defects, LCTRA improves the commercial yield by 12.5%.
And because the ILP is so incredibly efficient at utilizing the detours, it actually reduces the total number of spare TSVs you have to physically manufacture into the chip by up to 48%.
So you're saving massive amounts of physical real estate on the silicon while simultaneously making the chip highly resilient.
Exactly. It's brilliant.
Okay, so layer 1 is handled. We have a physical architecture capable of mapping its own damage and dynamically rerouting its neural pathways. But a robust physical chip doesn't mean much if the data flowing through it just gets intercepted or compromised, right?
Right. Which brings us to the second layer of this full stack synthesis hardware security primitives.
Because these edge devices, operating out in the field, they need secret cryptographic keys as their ultimate root of trust.
Absolutely. And to generate a key that a hacker can't simply reverse engineer,
Well-
you need a true random number generator, a TRNG. You need actual physical randomness.
But the sources talk about this massive bottleneck called the analog burden. What is that?
Well, traditional TRNGs rely on capturing ambient analog noise,
Uh-huh.
like thermal fluctuations or oscillator drift.
Which requires complex, power-hungry analog to digital converters to translate that fuzzy noise into a crisp 1 or a 0.
Exactly. And those converters are bulky. Plus, they frequently suffer from logic bias, meaning they naturally produce slightly more ones than zeros, or vice versa, which completely compromises the cryptographic strength.
Yeah, and if you're designing, say, a microscopic medical implant, you simply do not have the physical footprint or the battery life to support a bulky analog to digital converter.
You really don't.
So here's where it gets really interesting. If computers are designed to be perfectly logical and predictable, how do you force them to be truly random without using messy analog noise?
That is the exact problem solved by the ACR30 digital TRNG in the precision node. It eliminates the analog components entirely by using an all-digital imperative.
Okay.
It relies on a Rule 30 truth table, which is a well-known Class 3 cellular automaton rule. Now, under normal circumstances, Rule 30 is perfectly deterministic. If you feed it a specific input, you will always get a specific, highly complex output.
Right, because computers are deterministic. You can't just politely ask a perfectly ordered digital logic gate to act randomly.
Exactly. So the mechanism they use to force this deterministic rule into actual randomness is just brilliant. They take the logic gates calculating Rule 30 and they physically remove the synchronous clock.
Wait, they just take the clock out.
Yeah. In standard chip design, the clock acts as the enforcer of order. It dictates exactly when every logic gate fires, ensuring they all stay in a rigid, perfectly timed rhythm.
So the ACR30 removes that constraint, forcing the logic gates into a self-timed, asynchronous closed loop.
Right. It endlessly feeds the output immediately back into the input as fast as the laws of physics will possibly allow.
I love this. It's literally like taking the metronome away from a massive orchestra and instructing them to play a hyper-complex symphony as fast as humanly possible, looping it endlessly with every musician just feeding off the speed of the person next to them.
That's a perfect way to picture it.
Eventually, the timing is going to totally collapse.
It has to, because if we connect this to the bigger picture, you invite the physical environment to interfere with the mathematics.
The environment.
Yeah. As that signal loops asynchronously at breakneck speed, micro variations in the ambient environment like imperceptible fluctuations in heat or microscopic changes in the local voltage begin to naturally alter the propagation delay of the XOR and OR gates inside the circuit.
Oh, wow. So the physical imperfections of the silicon itself start compounding?
Exactly. These micro delays compound recursively with every single cycle. And within nanoseconds, the circuit is pushed into a deeply chaotic metastable state.
Meaning the deterministic logic just degrades completely?
Completely.
Yeah.
It turns into unpredictable oscillation. The system is precariously balanced, rapidly flipping between 1 and 0, entirely dependent on physical, thermal, and electrical noise. And then the system simply sends a standard capture signal to latch onto that chaotic state, extracting an 8-bit true random number.
The engineering elegance here is just incredible. And because it ditches the analog to digital converter entirely, it shrinks the hardware footprint down to a microscopic 270 square micrometers.
It's tiny.
It's built from just 75 standard NAND gates, which is the only reason it can actually fit onto these highly constrained edge devices in the first place.
And look at the energy consumption, too. It uses a minuscule 0.33 picojoules per bit of energy while achieving a throughput of 1600 megabits per second.
That is absurdly efficient.
But from a security standpoint, the most critical metric is its resilience. Because the randomness is generated by asynchronous metastability rather than a fixed frequency oscillator, it is mathematically proven to be immune to frequency injection, power, and thermal attacks.
So even if an attacker purposely floods the device with heat or voltage spikes to try and manipulate it, the ACR30 suffers less than 5% entropy loss.
Right, it's basically bulletproof.
Okay, so layer by layer, our precision node is really coming together. We have a self-healing 3D routing matrix. We have zero burden, perfect cryptographic chaos securing the data. Now we finally arrive at the third layer, what is this machine actually computing?
Right, the algorithmic compute layer.
Yeah, and more importantly, how is it doing it without instantly draining the battery? We need to talk about AI parameter bloat.
This is a huge issue. Cyber-physical systems are increasingly required to run deep convolutional neural networks, or CNNs, right on the edge.
We're talking about complex architectures like ResNet running real-time image recognition or spatial processing.
Exactly. And the problem is that running a deep CNN on a small edge device drains power at just an unacceptable rate, because moving millions of parameters in and out of memory is a massive bandwidth bottleneck.
Right, and the traditional engineering fix for this is something called the vanilla grouped convolution.
Yes, the vanilla approach.
It tries to save space and computational effort by taking the input data and dividing it into isolated, separate groups. You process a fraction of the data in group A and a fraction in group B. But the glaring flaw in the vanilla approach is that it ignores intergroup correlation.
It completely ignores it. By locking these computational groups into isolated silos, they can't communicate with each other.
It's like splitting a brilliant team into isolated soundproof rooms to solve a giant puzzle faster. They end up duplicating each other's work and missing the big picture because they can't talk.
That's exactly what happens. They end up learning the exact same underlying features independently. They duplicate each other's work, which creates hidden redundancy, and that severely degrades the actual prediction accuracy of the AI model.
So to solve this, the precision node integrates Bayesian sharing grouped convolutions.
Right. Instead of isolating the groups, it introduces a Bayesian framework to allow them to structurally share computational knowledge without loading the parameters back up.
And the mechanism it uses to pull this off involves maximum type 2 likelihood estimation.
Which I know sounds impenetrable, but the mechanics are grounded in a concept similar to a group lasso algorithm.
Okay, what is a group lasso algorithm?
In statistics, a least absolute shrinkage and selection operator lasso is a method that promotes sparsity. It penalizes non-essential variables, essentially forcing less important parameters to shrink to exactly zero.
Oh, I see.
Yeah, so when applied at the group level, if a feature isn't universally important across the groups, the algorithm just zeroes it out.
Leaving only the absolute essential shared features.
Exactly that. It exposes the core traits that every group is trying to learn independently. And then the Bayesian framework dynamically updates the prior mean of these sharing kernels.
So it's adapting as it goes.
Right. Instead of fixing a rigid prior distribution, empirical Bayes estimates the hyperparameters directly from the data on the fly. It finds the core feature like, say, a specific edge or texture in an image, computes it once, and structurally shares it across all the groups.
The real aha moment for me here is how this translates to the physical hardware. The hardware isn't just crunching slightly less math, it is structurally routing memory accesses differently.
Yes. By utilizing this Bayesian sharing, you enable rapid reusing strategies directly at the hardware level.
So the actual number of times the chip has to fetch data from memory drops exponentially.
It plummets.
Mm-hmm.
You preserve the exact same predictive intelligence and computational fidelity because the knowledge hasn't been deleted, it's just been centralized. And the total parameters required drop by 93%.
93%.
Yeah. The blueprints show that a standard ResNext AI block, which typically requires 2,304 parameters, drops down to just 144 parameters using Bayesian sharing.
That is just a staggering reduction in computational weight. I mean, the battery life saved simply by not moving those thousands of redundant parameters across the chip is what makes the edge device viable in the real world.
Absolutely. And if you bring all these components back to the core philosophy we started with, the takeaway is so clear. Optimization cannot happen in isolation.
Which is exactly why the precision node is such a crucial blueprint for anyone looking at the future of tech. I mean, whether you're deploying a smart medical implant to monitor heart rhythms or an autonomous drone navigating a disaster zone, the success of your device relies entirely on this unified approach.
You have to have the whole stack.
Right. You need bandwidth, which is solved by LCTRA's graph theory routing bypassing clustered physical damage. You need trust, solved by the ACR30TRNG turning ambient physical flaws into perfectly secure keys. And you need efficiency, solved by Bayesian shared convolutions mathematically slashing AI parameter bloat.
It really is a full stack architectural synthesis.
So what does this all mean for you, the listener? It means the days of singular hardware breakthroughs are behind us. The future belongs entirely to this kind of unified blueprint.
It's a fundamental evolution in design. And, I think there's a really profound implication here when you step back and look at the entire synthesized stack.
What's that?
Well, we're engineering cyber-physical systems, that are now deeply optimized to utilize their own physical environmental flaws like voltage microvariations and ambient heat to generate their ultimate security.
Right.
And at the same time, they're using advanced algorithms to dynamically reroute around physical defects. They're actively mapping and healing their own structural brain damage when connections fail.
Wow.
So it makes you wonder, at what point does a complex stack of silicon stop functioning merely as a rigid deterministic machine and begin to genuinely mimic the self-healing, adaptive, and chaotic nature of a biological organism?